Thank you, Rakesh. Thanks for inviting me to this conference. The title of my talk is Building a Platform for Artificial Intelligence, but the question I was charged with is, what is the future of computing going to look like? Is that right? And I'll give you one low-dimensional projection of what I think the answer is. It's going to look like the thing that we're building. So I'll go into a little bit more detail later. Again, I'm part of this new group at Intel. The CEO of Intel purchased my company, Nirvana. Nirvana is a startup that was building a platform for artificial intelligence that includes silicon, software, vertical solutions for different domains, working with companies, research, and so forth. And he used this organization to seed AIPG, the Artificial Intelligence Products Group, which again is a vertical business unit for Intel. It's kind of the sign of the times that Intel, the iconic chip manufacturer, has an AI group that presents a holistic strategy for enterprises to rapidly adopt AI, because it's quite painful. So the answer to the question, I'll answer it now so I don't have to answer it at the end. The future of computing, the current state of computing, there's a major inflection occurring. Computers are being used quite differently than they were used just 5-10 years ago. I used to be a trader on Wall Street. I remember that solving conic optimizations, I think Bank of America is right outside, isn't it? Solving linear programs, computers were used, I think 30% of the world's compute was just to solve linear programs. Computers have been used throughout history to solve differential equations, serve up web pages, do a whole variety of things. Today, computers are being used to do learning and inference on data. There's large corpora of data sets, labeled, unlabeled, unstructured, structured. Computers are learning statistical models of this data and making useful inferences on this data. This is quite a change in how computers are being used. So as part of this change, my role is to help enable it, to support it, help you be part of this inflection. And I'll go into a little bit of details. So I'd like to start with a little bit of history. John von Neumann is a celebrated mathematician, physicist, invented the field of game theory, co-invented, has many accolades under his belt that are difficult to enumerate. But one thing I want to point out is one of the last things that he did in his life is he was preparing a lecture series that he was going to present at Yale. Unfortunately, he passed away before doing so, and it was published posthumously as this book, Computer and the Brain. And this is a really remarkable book. John von Neumann was very involved in creating the first computer, and the EDVAC in this picture is partly his creation 10 years prior, in 1946. He basically created the modern computer, and the von Neumann architecture is still what is running most of the world's compute. And is actually Intel's processors are somewhat along this line of compute. So at the time, in 1956, 1957, we were learning more about neuroscience. We were learning how signals propagate on individual neurons, Hodgkin and Huxley. We're building very primitive neural network models, McCulloch and Pitts. There are other people around, interesting people who helped build computers. Again, Alan Turing, and Claude Shannon, and other very interesting characters. So John von Neumann has spent the last 10 years building computers, essentially what modern computers look like today, and he started thinking about how the brain works. So the brain is quite different than a computer. It has, it's crammed with these neurons that have very elaborate dendritic arborizations. They're all very tightly interconnected. The signals are slow. It's very low wattage. He was trying to figure out how the brain could inform building the next generation of computers. So he didn't get to do that, but what I'm doing today at Intel is essentially scratching the surface of this problem. So it's 70 years later, but we are actually starting to do this, and this is actually what is going to drive the next, this revolution in computing to help this inflection happen. One other thing that I'd like to point out, so I'm just going to seed some idiosyncratic ideas that we'll hopefully address in the Q&A, is this idea that computation, there's various laws that are coming to an end. So I don't subscribe to this view. There's Dennard scaling, where power density, as you shrink transistors, is no longer scaling. We're having a hard time building smaller and smaller transistors. That's depicted on the top left. That's a transistor, and the yellow is the dielectric gate. and that thing is becoming a single atom thick. So how much more smaller can you make it? Well, it turns out you can actually get around this problem by building fins of insulator or drain material and wrapping your gate around it. There are ways around these problems, and there's several ways of addressing these problems. There's actually quite a number of ways to address things like in the bottom left. As you shrink, again, the transistors become highly variable. Each transistor is idiosyncratic. How do you manufacture a chip with 9 billion of these things that are all different? There's actually ways around that. Another innovation is stacking. Now, if you have a processor, you have many layers of metal, copper wires going through these layers of different thicknesses. This is to address a major bottleneck in designing processors, is that your communication limited. So that's been addressed. There's lots of ways to address these limits, and I'm very optimistic about the future of computing. We're going to see more innovation in this area in the near term. There's things under wraps at Intel I can't discuss, and there's things almost surely that we can't anticipate that will push things forward. I'm also mentioning this as I'm a neuroscientist, so I'm an outsider to this field. And in building and advancing computation, you really have to be cognizant about computing at all levels. So one of the challenges for me is to actually understand the physics of building devices. It's easier for me to understand higher level concepts. But again, someone like John von Neumann was very cognizant of these things. When he was building the first computers, he was also trying to understand how brains work at the very low level. So limits of computation, I would say we're not at the limits today. I actually disagree with my co-founder on this. This is interesting debates. So I was a neuroscientist. I'll give you some of my history and how I'm bringing it to Intel and how it's potentially going to help us in this inflection. What I did in my PhD work is I studied this material on the left. It's a mammalian cortex, visual cortex. I was sticking needles into this tissue and trying to understand how populations of neurons code and do computations. And I was trying to complete this mapping to go from cortex to machine learning models that I was learning about, things like relaxations of NP-hard problems and pretty interesting things that seem magical on the machine learning side, and trying to find evidence of that happening in the brain. This turned out to be quite hard, and it's one of my passions, but I put it, it's currently on pause. And instead, I approached the problem as follows. On the right, you mentioned neural networks earlier. So neural networks are becoming more predominant as better accuracy in solving machine learning problems and so forth. They're widespread in usage today. When I first started our company, Nirvana, they were not so much. So the idea here is to build the substrate for the problem, workload optimized hardware. We're building silicon for neural networks. And in the process of building this hardware, we're going to have increased speed, scalability, robustness, accuracy, reliability. That will be an enabling technology for this new form of compute. And one of the things that I'd like to mention is this idea of listening to silicon. It's kind of the thesis of our new group at Intel. We're building silicon. We want to use the representational capacity of silicon as advantageously as possible. It's a pretty crazy idea, but it actually comes from Carver Mead at Caltech, who mentioned this in the context of building neuromorphic computers. If you really understand the substrate, then you can really exploit it. So again, as an outsider coming into this field of building chips, I always ask, why can't we do this? Why can't we do that? There's potentially good reasons why we can't, but it's really helped move us forward. We are building a novel architecture for neural networks. Intel is building neural network supercomputers. It's kind of the sign of the times. So just again, some inspiration that I've had through my career. It's been somewhat odd, but I'd like to just mention it. I think this is really critical for advancing compute. So there was this gentleman, Paul Horowitz, is a professor at Harvard. He was actually my physics professor, and he introduced me to how to build hardware. So here so Paul is one of the leads in the SETI program, the Search for Extraterrestrial Intelligence, has been passionate about this area for a long time. And what he's done is he's built machines, new computers basically from scratch, even like soldering things remarkably himself. In the middle is one computer he built. It's called Beta. It's the billion-channel extraterrestrial assay. It's essentially a giant Fourier transform system that takes signals from a radio telescope and does spectrum analysis. So he had to build custom hardware to enable this. Otherwise, there was no computers then that could solve this problem. Here's another thing that was very inspirational for me, is this thing that almost surely no one has heard of here. It's called the ANTON supercomputer. It was a project that was started by David Shaw, who was a famous hedge fund manager. There's this company called D. Shaw in New York, and formerly a computer scientist, and someone by the name of Ron Dror, who was a neuroscientist, machine learning expert, didn't have a chip background. Together, over the last 16, 17 years, they built a custom supercomputer for simulating molecular dynamics. So let me just show you what that means. So here you have this molecule that's embedded in a bilipid layer, a cell membrane. It's a potassium channel. It's one of the key computational components of neuroscience, signaling on neurons. And this representation here, at this time scale, you can see that there's this gesticulations of these various arms. This simulation and this time scale and these biological properties of these proteins, you can only see them by building the supercomputer that can simulate at femtosecond timescales. So a lot of remarkable science has resulted out of this, but the basic idea was they needed to build something from scratch to solve this problem. Again, this is in the flavor of what we're doing at Intel, is we're building custom things from scratch, all the way from the silicon to vertical solution to enable this new form of computing, neural networks, deep learning, AI, machine learning. Okay, so now going to some more pragmatic things, like what is the state of AI today? What are we trying to build to perform computations more efficiently, help Intel's customers? It's a business. So the way I define AI, my working definition is that, again, we're doing learning and inference on data. We're building statistical models of data, and we're performing inferences on that data. The definition of AI has changed quite a lot in the last 10 years alone. If you look at this excellent textbook on AI by Peter Norvig and Stuart Russell, published, I think, 10 years ago, used in a lot of classrooms, the distribution of topics, and if you look at just a table of contents, there's very little about neural networks. So just in the last 10 years, deep learning neural networks have taken over. And I guarantee that the next 10 years will look very different than what it is today. It won't be deep learning. It will be something else that's better, that's potentially also like deep learning and neural networks, rediscovered things that have been in our academic literature in the past. But this is what AI is today. It's deep learning, some neural networks, some machine learning, reinforcement learning, and some other classical forms of machine learning. This is what's deployed at Google, Facebook, and increasingly in a vast array of industries. So what is deep learning? I'm not sure how familiar you are with the term, but deep learning is essentially a rebranding of neural networks. So here on the left, you see depicted layers of neurons. This layering is a critical component of building good deep learning models. And I'll just mention the most critical aspect of these things is representational power. That you can use these networks to solve quite non-trivial problems. You can use them to recognize one of 10,000 objects in an image. Cats, dogs, different kinds of cats and dogs, other things, where they are in an image, a whole host of things that are quite difficult computational problems that only are being solved very recently with sufficient accuracy to be relevant. So, and I also mentioned earlier, one of the theses of AIPG, our group, is to extract representational power from silicon. So this is a principle that we want to drive. We want it to use to make better technology. Another key aspect of deep learning is its ability to learn automatically in the following sense. On the left, you have a picture of one of my co-founders, Arjun. In the past, you had to build systems, machine learning systems. This is somewhat a naive and oversimplified accounting of events, but you had to build an image recognition system or face recognition system that had already an idea of what eyebrows are, noses are, distances between eyebrows. But with deep learning, you can essentially build an end-to-end machine that learns the structure, statistical structure of faces by itself. You don't have to do feature engineering. Another aspect of deep learning that is probably most relevant to businesses, I see a lot of suits here. Many of you probably work in business. Is that true? I think. So what's interesting about what's happened in the last couple of years and why this is really exciting is that these systems have surpassed, the performance has gone beyond a threshold that makes them relevant to be used in consumer devices, potentially to build engines that fly us all over the place with high reliability. Examples in image recognition, we're now at human performance for some arguably artificial tasks, as well as in speech. You have Amazon Alexa was mentioned earlier, and Cortana and other smart assistants. The speech recognition in these systems has become good enough to not frustrate my dad and mom, basically. So that's only happened recently, a major success. So quickly, I think you have all heard that AI it's in the press, it's in the media. Is it overhyped? Potentially, I don't believe so. I think there are material things happening. Industries are rapidly adopting this technology. It's critical in some cases for technologies from businesses not becoming irrelevant. The fastest adoption is in the consumer space. Google search uses deep learning, AI, as well as other forms of machine learning. There's the smart assistants. In the healthcare space, again, it's not hype. There's material things happening. People are taking pictures of the fundus of the back of your eye, the retina, and they're able to use convolutional neural nets to see onset of diabetes. There's this thing called diabetic retinopathy. We're able to do this better. It's helping people. It's a material advance. In the world of finance, I work with the Chicago Mercantile Exchange. We help them on issues such as analyzing the microstructure of their limit order book. But in finance, you can imagine in the next few years, you'll see autonomous agents that perform tasks like market making, optimal trade execution, as well as a whole host of other things. It's just starting to happen now, as well as in other areas. And then I'll just leave you with two key ideas. The first one is that at Intel, we're trying to make deep learning and neural networks a core technology, something like a database at an enterprise. So we're using this thing called the Google Brain model. Google Brain has this really wonderful group that they've built internally that is a group of engineers, data scientists, even hardware developers that basically provide deep learning as a service to the various services that Google has. We're taking the same model at Intel, and we're providing deep learning as a core technology, for example, at a bank, to do a whole host of things. So this is part of the strive to get this next stage of computing to happen, adoption, making it a core technology, making it pervasive. And then the second idea I'd like to leave you with is that machine learning is a lot more than doing multiplies and adds and doing neural networks and so forth. It's actually the little square in the middle that's that stuff. And this is actually a slide to me that the hard work I'm doing is actually a very small part of the environment and infrastructure that you actually have to build to be able to do compute, artificial intelligence. So what is the other stuff? You can read it yourself. Things like the infrastructure, serving up results, processing, storing data, lots of other things that are actually very good, well done with von Neumann architecture. So Intel CPUs are used everywhere in here. Potentially the ML code in the middle will be running using some other architectures. And in summary, I just wanted to leave you again with the main thoughts. There's von Neumann computers, and there's a brain. How do we use our knowledge of the brain? How do we take things that I potentially have learned as a neuroscientist to inform computing and help us with this inflection? The idea of listening to silicon, that you want to really understand the substrate to be able to build better computing. And then there's this main, just to preempt your question, the main change that's happening in computing, that computers are being used for learning and inference. Thank you.